This video will cover Trig P.10 and Pre-Calc 1.9 notes. This will be part 1 of the video. The topic for this video is dealing with inverse functions. So let's first define what an inverse is, and then talk about how do we calculate an inverse, and then how do we verify that two equations are inverse functions. So all that an inverse is a swapping out of the x's and the y's. So what the x equaled in the original equation is what the y value is going to equal in the inverse of the equation. And vice versa, whatever the y is in the first equation, the x will equal in the second, or in the inverse equation. So if you have a function, f of x equals 2x minus 3, remember that f of x is just a labeling mechanism. We define this function as the f function, but it is taking the spot of the y value. So you can replace that right away with the y. So let's do that, so that we can now swap out the x and the y values. So wherever you see the x, put the y, and where you see the y, put the x. So this is going to become x equals 2y minus 3. And my goal then is to be able to solve this equation for y, so now I have the inverse function. So for this problem, we'd have to move over the 3. And get rid of the 2. So we would say that x plus 3 divided by 2 is equal to y. But to truly show that this is the inverse of the f function, we don't want to leave this as the y. We want to change it back to our f of x. But we don't want to label it as f of x either, because it's not the f function, it's the inverse of the f function. So the way we show that notation is we do f raised to the negative 1 of x, and that is inverse notation. So it would really say that the inverse of f is equal to x plus 3 all divided by 2. So again, I've written the steps over here for you so you can kind of see it's really a 3-step process. Get rid of the f of x, or whatever that is. If it's an f of x, a g of x, or an h of x, replace it with the y. Swap out the x's with the y's, and the y's with the x's, and then solve your equation for y. And don't forget to use the inverse notation when you're all done. The next concept we're going to deal with is verifying that two equations are a function and then its inverse. And to be able to do this, what we need to do is we need to go back to what we learned in the last lesson, which is composition of functions, where we put one function inside of the other function, and then we reduce that. And when we do this with inverse functions, what should happen is when I do f of raised to the negative 1 of x, so when I put the inverse into the f function, and when I put the f function into the inverse function, I should be able to show that they both reduce down to be an x. So let's do that. Let's first find f of the inverse. So take your inverse and put it into the f function. So that would look like this. 2 times x plus 3 over 2, and then minus 3. Now when I reduce this, I should get it to be just an x. So I know what will happen first is the 2's cancel out. Then I have x plus 3 minus 3, and those cancel out also. So I got that to be an x. I need to do the same process again, just backwards now. Plug the f function into the inverse. So plug this into here. And hopefully when I do this, I'll show that it reduces down to an x as well. So let's rewrite this. Instead of x plus 3, it'll be 2x minus 3, and then finish writing this out. Plus 3 all divided by 2. Alright, so algebraically the 3's will cancel each other out, and you'll have 2x over 2, and now the 2's cancel each other out, and you're just left with an x. Now usually what will happen when I ask you to verify, so the instructions for this one were a little bit different than our previous example. Our instructions in the previous example said to find the inverse. If you already have the inverse listed up here and you want to show that it actually is the inverse, then you need to verify, and you need to show that they both equal x. It is not enough to take the f function here, flip-flop the x's and the y's, and solve it for y and check to see if you get that. But that seems to be usually what a lot of students will do to solve these problems, and you can't, to truly verify that they are inverse functions of each other, you can't do that. You can't just check to see if you get the same equation. You have to do this. You have to show that when you do composition of the function, putting f inverse into the f and putting the f into the inverse, you get it to equal down to be an x and an x. So pay attention to the instructions. If it says the word verify, you want to show that both equal x when you've reduced them. Okay, for our next example, I want to talk a little bit about the relationship between the domain and range of a function, and then the relationship that it has with the domain and range of the inverse of the function. So what I've done so far is I've got two different graphs up here. Let's just right now focus on the red graph, and the red graph is the original function. So I plugged in y equals 2 over x minus 5, and I get this. So what is the domain of this function? Well, remember, the domain are the x values that work. So looking at this, it appears that all these negative x values work for this red graph, and they keep working until I get to an x value of a positive 5. And then, you know, at 5.1, 5.2, 5.3, 5.4, and so on, all the x values greater than those are working as well. And it should make sense that an x of 5 doesn't work, because if I put a 5 in here, I end up getting a 0, and I can't do 2 divided by 0, that's undefined. So the domain would be x is all numbers except for 5. So we can write that as x does not equal 5. The range, notice that the range would be the y values, and the graph is below the x-axis here, and then it comes above the x-axis here. So the only y value that's not working is the y value of 0. So y cannot be equal to 0. All other y values are working here. Now, the other graph that I have on here is the graph of the actual inverse of this. So first thing I want to do is I want to calculate it so you can see how I got that. So let's find the inverse. So what we're going to do is we're going to flip-flop x's and y's. Actually, first I'm going to rewrite that with a y. And now if we flip-flop, we would get x equals 2 over y minus 5. And now we have to solve this. So we'll solve by multiplying by y minus 5. So we would have x times y minus 5 equals 2, because these would cancel out. Get rid of the x by dividing. So y minus 5 is equal to 2 over x. And get rid of the 5 by adding. We'd find then that our inverse would be 2 over x plus 5. And we should really label that with inverse notation. So let me change that to inverse notation. So that's the equation for the inverse that we're looking at. And you'll notice that I already have that up here in the diagram. So I've looked at the equation here for the graph of the inverse. Let's go back and look at what domain values work and what range values work. So notice now that the x values that are working are all of these negative x values until I get to an x value of 0, and then all these positive x values are working. So this time the domain is x does not equal 0. And the range might be a little bit more difficult to see. But what I want you to notice is that if I was to draw a horizontal line here and here as best as I can, notice that the graph is approaching that line, but it doesn't really touch it. Same for this side. The blue side is approaching that, but not really touching that. And it's going through right at a y value of 5. So all other y values are working except for 5. So we would say then that the range of the inverse graph is any number except for 5. Well, now let's look at both of those together. Notice that the range of the function and the domain of the function are the same in terms of not being equal to 0, just the variable is different. Same thing for the domain of the function and the range of the inverse. That they're the same, they can't be equal to 5, except for the variables are different. So what we can show here, is based upon this example here, we can show that the domain of the function and the range of the inverse are the same. We've just shown that here. and the domain of the inverse and the range of the function are the same. So that would be showing this portion. And that's going to be a common trait that you're going to notice with the graph of a function and its inverse.